Okay, guys, discrete optimization, these are the advanced topics now. They are beautiful. You should really look at them. But, they are really the advanced topic of this class, not strictly mandatory in a sense. But, they're really nice. So please look at them. So I'm going to talk about column generation, okay? And I'm going to give you a big kind of one-slide introduction to tell you what the spirit of it is. And then I'm going to show you the original example where this was introduced, which is cutting stock, okay? So in a sense, you can think about branch and cut as we are going to solve this MIP, which has an exponential number of constraints. But of course, we don't explore them all. We generate them, one at a time, okay, on demand based on the value of the linear relaxation. Okay, so in the particular TSP, we were generating these sub-2 constraints or these comp constraints on demand. Okay, column generation is just another. It's the same idea but reverse, right? So instead of having exponentially many constraints, we're going to have exponentially many variables. Okay, and so we want to solve this LP with exponentially many variables. Okay, wow, that looks crazy, right? But of course, we won't list all these variables. We're going to generate them on demand again, right? And so the key point here is that the variables are going to represent complex objects, not the simple decisions that we had before. And I'll talk a little bit about branch and price, which is kind of the use of column generation in branching scheme at the end. But the key idea would be essentially to do a branch and bond, but using column generation at every one of the nodes. Okay, so this is the cutting stock example. Once again, it came from Gilmore and Gomery, the same Gomery as the Gomery cuts, of course. A lot of contribution to combinatorial optimization. And this is what the problem consists of. So you have large, wood boards, okay, really large, okay, of a particular length, okay, and you have a large number of them, and you want to cut them into small shelves of different sizes, okay, and these small shelves are what your customer requires. They don't want very long thing that they have to cut at home. They want the right, more or less the right size, okay, and so for every one of these different types of shelves, okay, so you have a demand of the particular customers. You have the length of this shelf and then the demand of the customer, okay. And so what you need to do is to find how many boards, big boards, you need to actually meet the demand of your customers, and also you want to know how you have to cut the big boards to actually get to that solution. Okay, so that's the problem. Okay, I'm going to show it visually because it's much more, much clearer visually. So these are the big boards. Actually, they are not that big in this example, but these are the long boards. Okay, and these are the types of shelves that you want to cut. Okay, so this board here is a length of 110. Okay, and so the smallest shelf here is size 20. The largest is 75, and there are a variety of other sizes in between. Okay, and so for every one of these guys, you will have a demand. Okay, your customers want 48 of these small shelves. They want 8 of the longest shelf. Okay, and so you want essentially to meet the demand of your customers, and you want to know how many of these big boards you want and how you cut them. Okay, so this is a particular way to cut them with 2 of the shelf size, size 20 and 75, and obviously the sum of this is 95, so it fits in the big board. It's one of the valid cutting. This is another cutting which is 105, 50 and 55, and this is another cutting 20, 20, 20, 20. Okay. And so basically what you want to do is look at the various way you want to cut these boards such that you minimize the number of big boards that you are using. Okay? So this is the first MIP model that I'm going to show you. It's going to be a terrible model, okay? But it's the first model that comes to mind, right? So what you want to do is you want to decide if a particular board is selected in the optimal solution or not, okay? So board B is going to be selected, okay? And then you will have a particular variable XSB, which is going to tell you how many shelves of size S are basically basically available from the cutting of board B. Okay, so if you have, for instance, 20, 20, 20, 20, that's 4 times, well, let's say 5 times 20, that's going to tell you that size 20 is cut 5 times in this particular board. Okay, so you have 5, shelves of size 20 in that board. Okay, now the constraints that you will have to express inside the MIP are going to be, the typical constraints that you have in, when you have these 2 types of variables. One of them is going to say, oh, I can, the board has to be cut, if I actually, board B has to be cut if I'm actually, delivering some shelf from it. Okay. The second thing that you want is to make sure that the sum of the things that are basically cut from a particular board don't exceed the size of the board, and then you have to meet the demand of the customer. Okay. So, and the objective, of course, is to minimize the number of boards. So this is a MIP, okay, which is describing that, okay. So you look at the board, okay, the set of boards, okay, and you basically minimize the number of them that you select, okay. Simple objective function. These are 0, 1 variables, whether I'm using board B or not, okay. Now, if so the first set of constraints is basically telling you that if you are not using board B, you can't cut anything from it, okay? That's what this constraint is using. We use a big M notation. Then you basically have, X, YB, multiplied by M, and that basically constrain the value YB multiplied by M, and that's constrain the value of X SB. So if YB is equal to 0, XSB has to be 0, okay? The second type of second set of constraints that you have there is basically the capacity constraints. For every bin, if you sum the set of the if you sum the set of the the shelf that you are cutting from this board, it has to be smaller than the length of the board, okay? And then you have essentially here the constraint that's saying that you have to meet the demand, and then you have basically the 0, 1 variables that you have there, okay? So this is the first model that comes in, to mind. And one of the things that you see here is so you see, all the types of constraints, and you can wonder, is this a good model or not? Okay, and the answer is no. This is a terrible model. It has a very bad linear relaxation. Okay, and one of the things that you can notice immediately is that it will have a lot of symmetries. Okay, so essentially all the boards here, okay, all these boards are basically interchangeable, which basically means that if I have a cutting with some of these boards, I can just permute this and I have another, another set of boards. And as soon as you have something like that in a MIP, it's terrible because the MIP can't even if you have a good bonding, you still have to explore this, redundant solution. So you will have to try to break these symmetries as well. So this is a very bad model actually, okay? Now, one of the questions you may ask yourself is that, how many boards do I need, okay? Now, there is a very simple upper bound of the number of boards that you need, and you just sum, the demand. And in the worst case, you would have one board for every one of the demand, okay? So in a sense, there is an easy upper bound for every one of these things. But even with that upper bound, this is a very bad model, okay? So what we're going to do is, move to hyperspace, okay? So like in Star Wars, okay? So we are going to change completely the way we view this problem, okay? And instead of having this binary variable, 0, 1, whether I use that board or, how many items, how many shelf of that type I'm cutting in that board, I'm going to reason about cutting configurations, okay? So I'm going to say, okay, this is one way of cutting this board, okay? How many of these guys do I select? So I'm not looking at very simple object here. I'm going to look at really complex object that tells me how I can cut the big board, okay? And so once you have that, okay, so you will decide which of these cuttings you will select to meet the demand, okay? Now, how is one of these configurations selected or represented or characterized? Essentially, what you have to say is that, this is a configuration that cuts this amount of shelf 1, this amount of shelf 2, this amount of shelf n, and so on. Okay, so what you need to do is basically specify only, I have a cutting. This cutting is providing me that many shelves of this type, that many shelves of that type, and so on. Okay, that's what I'm going to reason about. Okay, so every one of these configurations is basically telling me the various shelves that I get from it. Okay. And so we can find all these configurations. Okay, we're going to discuss how to do that, but we can find all these configurations. Okay, and so now instead of reasoning about whether I how many is this board used and how is how many of these type of shelves are cut in the board, I'm really using this configuration. I don't want to reason about these cuttings anymore. I'm just reasoning. I have them. I'm just reasoning about which configuration I'm going to select. Okay, so the decision variables are going to be, for a particular configuration C, XC, okay, that's going to be the decision variable, and XC is going to denote how many times in the optimal solution, okay, or in a high quality solution, I'm selecting that particular type of configuration. Okay, so this is the model, very simple. Now, we got rid of all these variables. Okay, so what we are saying here is that we want to minimize the number of boards that we cut. Okay, that's XC for every one of the configuration. How many of these do I select? You take the sum of these, and you want to minimize that. Okay, minimize how many of these a configuration I'm selecting. So that's what you need to think about them. Okay, so this is the number of configuration of type C. Okay, the sum is the total number of configuration that I'm cutting. I want to minimize that. Okay, and then you have only really one constraint. Okay, which is how many I need to meet the demand, okay? And how do you do that? Well, you have the number of configuration of type, of type XC that you are cutting, okay? For every one of the type of shelves that you are requesting, it's going to, give you a number which is NCS, okay? NCS is telling you the number of shelf of type S that configuration C is providing, okay? So if you multiply these two, you have the number of type shelf of shelves of type S that are produced by all the configuration C that I'm producing, that I'm cutting, and then that has to be greater than the demand for shelf of type S. Okay, and that's what this constraint is doing. So once I have this configuration, I want to minimize the number of them, okay, that I'm selecting, and I want to meet the demand, okay. And obviously, these values have to be integers, okay, the number of shelves that I'm cutting, okay. So this is a much simpler MIP model, okay. It has also a very strong relaxation, okay? And so one of the things that you have to see here is that we got rid entirely on the capacity constraints on the big board. Why? Because they are built inside the configuration. My configuration are valid cuttings, okay? So I know that these are good cuttings, okay? They are valid cuttings. They are cutting the big board, okay, in pieces, okay? And the only thing that I'm doing is really selecting which one I want. Okay, and then there are no symmetries here. All these configurations are different. I'm just picking the right subset of configuration. So I got rid of all the symmetries. I got rid of all the capacity constraints, and I have a beautiful, strong relaxation. Okay, now I told you that we move to hyperspace, right? So we are basically looking to this, the cutting configurations, okay? Not simple, 0-1 variables, okay? How do we find this configuration? The only thing that we need to do is basically satisfy these capacity constraints. Every one of these configurations, when it provides a number of shelves of different types that it's providing, has to satisfy this configuration. And this is a very simple constraint, right? So if we are trying to characterize a configuration, okay, we're going to look at this number, NS. Okay, so how many of shelves of type S are we producing in that configuration? And we obviously want to make sure that when you take this type S, multiply by the size LS, you want to be sure that you are smaller than the length of the big board. Okay, so every one of these configurations is going to satisfy that. Okay. So we could enumerate them all, right? So it's very easy to find. This is kind of a simple knapsack constraint with no objective, right? So we could enumerate all these constraints, but in a practical problem, okay? So you will have billions and billions and billions of them, right? So, and we can't generate them all at the beginning and just solve, the mid problems that I've shown you before. So what we're going to do is, the same trick as we did for branch and cut. We are going to generate this configuration, one at a time, on demand, okay? So we're going to solve the linear relaxation, and then we're going to say, ooh, can I improve this linear relaxation by generating a new configuration, okay? And so this is the essence of column generation. It's basically saying, ooh, what is the next configuration? Or in terms of the linear programming relaxation, it's going to be, what is the next column that I have to generate, okay? So this is the tableau at a high level, right? So you see in this particular case all the variables which represent the configuration. So every one of these columns, in a sense, is a configuration. And that configuration is telling you, how many of these types of shelf, we are producing. Okay, in that particular configuration. So in a sense, this big matrix here is telling you, for a particular configuration, how many of these various types of shelves I'm producing. Okay, and of course the decision variables are these xi, how many of these things we do. And obviously when you try to have the constraint that you are representing is that the sum of these guys on a particular row has to be greater or equal to the demand. Okay, so let's say that we have a bunch of configuration, we solve the LP, we get a good value. Okay. Okay, and then you say, ooh, can we improve this linear relaxation? And what you do is basically saying, ooh, can I find a new column, which when I add that column, okay, I'm going to get a better linear relaxation. Okay, so you don't want to generate arbitrary, configuration. You want to generate some of them that will improve the value of the objective function. Some of them may be completely terrible. They are cutting things that you don't need. You want to just to look at the particular configuration that, because they have a good mix of different types of shell, will improve the linear relaxation. Okay, that's the goal. Okay, so how do we do that? Okay, so essentially, a configuration is a column inside the linear relaxation. Okay, so what is an interesting configuration? Well, it has to be a column whose variable, when I'm adding it, inside the linear relaxation is going to enter the basis, okay? It's going to improve the linear relaxation. If it's not entering the basis, why would we put it in there? If it's already optimal, we are adding a column, that's basically not entering the basis. It's going to stay at the same place. That's terrible, right? So what you want is to add this column such that it enter the basis and improve the value of the linear relaxation, okay? So essentially because we covered linear programming before, we know that to do that, you need essentially a configuration with a negative reduced cost, okay? So if it's positive, it's not going to enter the basis. You want a negative, reduced cost. What is this cost? This is the ugly formula that we saw in linear programming. Actually, it's beautiful, but, it's kind of messy. Okay, so we're going to ignore the constant term. We're going to look only at this term. Okay, so let's zoom on it. Okay, so this is the part of it which is really interesting. Okay, the constant part we are not interested in for generating the new column. You look at this thing. Okay, you specialize it to the problem, which basically means that the constant here, the C, is going to be 1. That's the cost of one particular configuration. Okay, they are all the same, these boards. Okay, and then this is the configuration, right? So the configuration is going to specify, okay, how many of the various types of shells we will be producing, okay? And then you multiply that by CB and the inverse of the basis, okay, at this point in the linear relaxation, okay? So we are looking at this thing, okay? So but what is this guy? So, okay, we know this guy, right? So we know that this is essentially the simplex multipliers or the dual variables of the current linear relaxation, okay? So when we are looking at this is essentially what we will want to become negative. Okay, we will want to find a configuration here, which produce these different types of shells, which when multiplying by the multiplier are going to make this whole expression negative such that it entered the basis. Okay, of course I don't know this n, so this is what I want to compute. I want to compute this really nice configuration such that this expression using the dual variables are going to give me a negative number such that that configuration is going to enter the basis. Okay, so in a sense, these multipliers, these simplex these dual variables, I have them. Okay, they are already inside my tableau, right? So I told you how to get that when we talked about linear programming. So I have these guys, okay? So I'm looking at defining these values here. I have these guys, and I have 1, okay? And I know I can try to find these n's, using this, dual variable such that I will be able to have a configuration which enter the basis, okay? So what I'm really doing here is solving an optimization problem, right? So I want these two conditions. I want, a valid, cutting of this board, and I want, that particular cutting, that particular column to enter the basis as soon as when I put it inside the simplex tableau, okay? So the feasibility is what I told you before. I told you that we could generate billions on billions. They have to satisfy this constraint, which basically means that the cutting is valid. This ns times ls, when you sum them, have to be smaller than the big board, okay? And then I have this quality criteria, which says, this ns that I'm looking for, when I use the dual variables, when I compute a reduced cost, these reduced costs have to be negative, and therefore this particular configuration is going to enter to the basis, which means we're going to select that configuration, right? And so what you end up doing is solving this beautiful, optimization problem again, okay? And so this is a problem here where we are basically solving, so we are basically minimizing the value of the reduced cost, okay? So we are trying to meet, the capacity constraints, or the way you are making sure that we are cutting this board, in the right fashion. And obviously this ns have to be integer values. So this is a MIP problem that we are solving. Okay. Now if we optimize this, okay, if we optimize this MIP again, okay, and the value is negative, then we know, okay, that we have a column that's going to enter the basis. So great. Okay, so we have a new variable in a sense, okay, which will enter the basis and improve the linear relaxation. Okay. Otherwise, that means that none of them exist. You could add, exponentially many of these things, these billions of things that remains. You will never improve the linear relaxations. That means that you have the best linear relaxation at this point. Okay. So now look at this MIP problem. Okay, can we solve it efficiently? What does it remind you of? Once again, this is going to be an abstract problem, okay? And so we can solve this problem very, very quickly. And therefore, essentially generating a new column here, which can enter the basis, is going to mean I have to solve this knapsack problem. And once again, we are basically closing the loop with the first lecture, right? So this is how you do column generation then, okay? You generate an initial set of configuration. For instance, you can use one configuration for each shelf type and try to pack as many shelves of that type, okay? Then you solve the linear program, okay? So you're using the existing configuration. If you have an integer solution, obviously you stop, okay? Otherwise, what you're trying to do is basically trying to see if you can, find a new column, find a new variable that will improve the linear relaxation. To do that, we have to solve this simple knapsack problem, okay? And so if you find this new column, okay, you repeat at step 2, and then you continue improving the linear relaxation, adding more and more and more variables, okay? Now, once you can't do that, okay, so what you do essentially is that one of the things that you can do, and you do for cutting stock because the linear relaxation is very strong, is you simply round up all the value of the shelf of the n variables, okay, because essentially, that will increase a little bit the number of shelves that you cut because these variables can be fractional. Okay, so this is an example. Okay, so we basically have this big board. You have the various demands for the various types of shelf. Okay, we start with a very simple set of configuration. Okay, we take shelf of size 20. We cut as many of them as possible. We do the same thing for 45, for 50, 55, 75. Okay, so these are my set of initial configuration. I solve the linear relaxation. That's going to select a mix of these things. Okay, and then I start doing the column generation. Can I add new configuration that's going to help me improve the value of the linear relaxation? The first one that I will find is something that cuts 20 and 75 at the same time. Then something that cuts 20, 45, and 45. And then another one, which is 20, 20, 20, 50. Okay, that's a nice one because it cuts the board perfectly. And that's going to be enough to actually find the optimal solution to this linear program with exponentially variables. This is the value of the objective constraints. This is what you are cutting for every one of these typical configuration. You see that some of them are fractional, right? So for finding a feasible solution, you will have to round that up, okay? Which means that in this particular case, the value that we'll find, the integer solution is going to be 48, okay? This is obviously a lower bound, okay? Now, if you try to solve this problem optimally, okay, this is what you get. Okay, so this is the first, let's say you use the first formulation that I've shown you to solve it optimally, you would get 47. Okay, now what is interesting is the time. Okay, the column generation on this very, very tiny example, right, is going to take 0.03 in one of the systems that we are using. Okay, the MIP system, the first MIP formulation is going to take about 4 seconds. That's 2 orders of magnitude, right? And so that's essentially the basic feature of column generation. It's a very nice technique for scaling up to very large, for large-scale problems. Okay. And so that basically gives you the essence of column generation. If you want to do branch and price, it's the same idea, except that column generation is at one particular node of the tree. Okay? So in a sense, you have to think about column generation is giving you a very, very good lower bound at every one of the nodes by generating variables on the fly. Okay? And as soon as you do a branching decision, you can start regenerating new column, okay, for improving the value of the linear relaxation. Okay? So you basically iterate, branching and then doing column generation to find a really nice lower bound a very nice lower bound or upper bound, a relaxation, a very good relaxation to the particular node. Okay, so this is column generation, branch and price, very useful in practice. There are a lot of extension to these things in practice that work very well in different settings. It's a very interesting setting when you have different kinds of complex objects that you have to manipulate. Okay, thank you very much. Next lecture is going to be on large neighborhood search and scheduling.